Fisher of Indiana University, Bloomington, USA, and he will be speaking on arithmeticity, superrigidity, and totally geodesic manifolds. Professor Fisher.
All right, now I have to remember how to get this. There we go. Sorry, that took me a second. I first want to say that I'm honored to be here and speaking this morning at this conference in honor of Raghunathan, who is one of the great heroes of the area of mathematics in which I've spent my career working. And I am only sad that we cannot all be together in Tata for this occasion, partly because I've never been and would love to come sometime. All right, so as Venki said, my talk is on totally geodesic submanifolds, superrigidity, and arithmeticity. And I'm going to start by stating a slightly strange form of the main result, just to allow me to motivate some history. So I'm going to let x tilde be an irreducible symmetric space of non-compact type with no Euclidean factors. I'm assuming this is one of few places where I can say this and not be too concerned, but it will be specified to real hyperbolic space for much of the talk, so don't worry if it's not something you like. X will be the quotient of that by some group gamma, some discrete group gamma that has finite volume, and we will assume that gamma is irreducible or that the quotient is irreducible. And again, don't worry if these are words you don't like. You can think of a finite volume hyperbolic manifold if you prefer. And now the theorem that we proved is in some sense the following. It says if X contains infinitely many maximal closed totally geodesic submanifolds of dimension at least 2, then this group gamma is arithmetic. And now I should, for the students in the Zoom, maybe run over some of the definitions in this theorem. The experts already know them. Maximal is what you think maximal means naively, which is just it's maximal if it's not contained in another object of the same kind. So a totally geodesic submanifold is maximal if it's not contained in another proper closed totally geodesic submanifold. This is just to avoid stupidities. It's it's important that you make this assumption, but it's just to avoid certain examples. And as I said before, you can always think that X tilde is hyperbolic space if you prefer. Then results will really only be new and real and complex hyperbolic space. And you can also think of this theorem the other way around, which is important for some purposes, which is instead of thinking of it this way, you can think that, well, if gamma is not arithmetic, then we only have finitely many maximal closed totally geodesic submanifolds. And sometimes it's better to think of it that way. And just the other reminder is that G, which is the isometry group of X tilde, is a semi-simple Lie group. Gamma in G is a lattice, i.e. a discrete subgroup of finite covolume. And arithmetic means that there is some number field K, so that gamma is commensurable to the integer points over that number field in G. And of course, I could be more pedantic and insist that there was some K form of G such that this was true, and the experts can bother me about such things, and those who aren't deeply already schooled in them would not get much out of my being more pedantic at this moment, so I won't be. The experts know what I mean. The non-experts should think, oh, I'm just thinking about the integer points, the Z points in G, which I'm thinking about, perhaps naively as a matrix group. All right, so as I said, this theorem stated this way is not really our theorem in some sense, because a lot of it follows from work of other people. And I'm just going to start by telling you some of that history, because it also inspires both the result and the techniques. So if X has higher rank, which in this context, I can say if X tilde contains a totally geodesic copy of R squared, then Margulis already proved in 1974 that gamma is always arithmetic. There's some history of that result as well as some contributions of Raghunathan's that I don't have time to dwell on today. But we'll start history in 1974. If X is quaternionic hyperbolic space or the Cayley hyperbolic plane, then Correlette and Gromov-Shane also proved that X is always arithmetic, or really I should be saying here gamma is always arithmetic in the definitions I gave, but that's okay. So what's left of the theorem after you take their results for granted is that the theorem is about real and complex hyperbolic manifolds of finite volume. And for us, this is important. You know, there are theorems in this context where you could give a proof for a general X or X tilde. We really need the specific structure in the proofs in various places. We need these to be real and complex hyperbolic manifolds. And this, in that context, and really in, you know, the history of this is also a bit complicated. This answers a question that was asked by Alan Reed and Kurt McMullen in various forms in the mid-2000s. You know, maybe we're answering a question that's slightly more general than what they answered. But I mean, we're answering a question that's slightly more general than what they asked, but they more or less raised this question. And one of the key motivations for this is Margoulis's commensurator superrigidity and arithmeticity theorems, you know, the first of which is, you know, there's this superrigidity in higher rank, there's this superrigidity and arithmeticity theorem for groups with dense commensurators, which I'll talk about in a moment. And the key observation here that makes this, you know, theorem plausible in the first place is that if the commensurator of gamma is dense, then if I have one totally geodesic submanifold, I get infinitely many. And so I just want to explain these last two sentences a bit. I think it's on the next slide. Yep. So let's say that G is the isometry group of this X tilde, and gamma is the lattice. And then we let the commensurator be the set of elements of G such that when I conjugate gamma by G, I get a group whose intersection with gamma is finite index in both gamma and the conjugate. So, you know, this is the definition of commensurator. You know, it's that the conjugate has finite index both in gamma and in the conjugate. And Margoulis's other theorem also proved at the same time in 1974 is just that if the commensurator contains gamma at finite index, then at infinite index, then gamma is arithmetic. And actually the converse came earlier and was due to Borel, and sort of the example is, you know, if we take everyone's favorite lattice, at least in this room, which is S ln Z, and we look at its commensurator in S ln R, what you get relatively easily is the Q points in that group. And so this is an example of infinite, you know, of commensurator that contains the group at infinite index, and this is clearly an arithmetic group. And, you know, Borel's proof requires more work than this one observation, but this is essentially why it's true. And, you know, all of this, I find this somewhat hard to understand from the algebraic viewpoint, so I like the geometric one better. And that is that if G commensurates gamma, then G is an isometry of a finite cover of X, right? The covers of X have isometries that come from deck group elements. And what this is saying is that somehow we get extra isometries at finite covers that come from the commensurator. This fact is an easy exercise in covering space theory to check. And so now I'll tell you Reed's idea of why dense commensurator implies lots of totally geodesic submanifolds. We just pick one up. We pick up a totally geodesic submanifold in X. We lift it to a cover X prime, some finite cover X prime, where some element G in the commensurator is an isometry. We push M by this isometry and we push it back down to X. And it's a more or less trivial exercise to check that when you do that, you get a new totally geodesic submanifold. So any totally geodesic submanifold in the presence of dense commensurator gives rise to infinitely many. And in fact, you know, the easy exercise that I forgot to state is that once the commensurator contains gamma at infinite index, it's not hard to prove that the commensurator is in fact dense. and that's easier to prove than it is than as arithmeticity is to prove. But so you have density here, and therefore you can move this around in lots and lots of ways once you're in this setting of being arithmetic and having dense commensurator. So I want to give a little more history, and this is probably the funniest thing that's happened to me in my mathematical career is this problem had been around for a while. I only learned of it in 2016. In the summer of 2016, I learned of it from both Agel and Stover, probably 3 weeks apart. Both of these guys told me this problem, and nothing was really known for a really long time. And then in 2018, with a slightly different author list with Lafont instead of Bauder, we proved some first cases of this, where really what we proved is that the Gromov, Piatetsky, Shapiro examples of hyperbolic manifolds, of non-arithmetic hyperbolic manifolds, had only finitely many totally geodesic submanifolds. And really at essentially exactly the same time, Benoit and O didn't prove this, but they also had in at least the three-dimensional case, there was a key ingredient in this proof that they discovered independently at the same time. And they probably would have noticed it. It implied at least the three-dimensional case of our result, without my pointing it out to them relatively quickly, had I not pointed it out to them. And then in 2019, with Bauder, Miller, and Stover, we proved the real hyperbolic case. And again, more or less at the same time that Margulis and Mohammadi proved the three-manifold case. We were, I think 4 or 4.5 weeks later to the archive than they were. The works were independent. But I've never encountered competition in my life before mathematically, and this was happening routinely on this problem. And then in 2020, we proved the complex hyperbolic case. And again, there it's a little, they did again beat us to the archive, but it's clear they'd heard talks about our work before they archived theirs. Baldi and Olmo proved special cases of this result, as well as proving a number of other interesting theorems. And this one is perhaps the most interesting bit of competition, because while everybody else on this slide is probably familiar to everyone here, Baldi and Olmo are doing this using, Olmo has some homogeneous dynamics contributions too, but they were really proving this theorem, their cases of this theorem entirely by different methods, using algebraic geometry, O-minimality, and Hodge theory. And so it's very interesting that the theorem has two different proofs from entirely different worlds at that in those cases. And now, rather than dwelling on the rather intense competitive environment I lived in for 3 years while working on this, I want to talk to you about a little more longer view of history about why we care about totally geodesic submanifolds and hyperbolic geometry, and more context for these results. And so the first use I know of totally geodesic manifolds and real hyperbolic geometry is that the very first examples of real hyperbolic manifolds of dimension n with positive first Betti number in all dimensions were due to Milson, and he very much used the presence of totally geodesic manifolds. He even used the fact that there were a lot of them, and used various versions of the same tricks Reed was using in the observation I gave. Before that, there had been finitely many earlier examples of manifolds with this Betti number, but those were also all built. Those were all built by Winberg as reflection groups, and again exploiting the. In a reflection group, you have the mirror of the reflection, and the mirror of the reflection is a totally geodesic submanifold, and will end up closing in the quotient. And so Winberg was again exploiting totally geodesic manifolds. Of course, in the context of any conversation about arithmeticity, the really important thing that occurred was in 1988 in work of Gromov and Piatetsky Shapiro, where they constructed infinitely many non-commensurable, non-arithmetic hyperbolic manifolds in all dimensions. And they did this by a cut and paste construction along totally geodesic submanifolds. So, totally geodesic submanifolds played an important role in hyperbolic geometry. And variants of these Gromov-Piateski-Shapiro manifolds have been discovered and discussed and used for various things by numerous authors. I list here only Agel and the Seven Samurai, which isn't even, really listing anyone, because I don't know if that's the way in which Saki Galander refers to his paper with 6 co-authors whose names don't fit on the slide, but I don't know. I hope it means something to many people. My favorite recent application of this trick is the Galander-Levitt theorem that says that in a very precise sense, most compact or finite volume real hyperbolic manifolds of dimension at least 3 are non-arithmetic. And part of why I like this theorem is because combined with our theorem, it says that most compact or finite volume real hyperbolic manifolds have only finitely many totally geodesic submanifolds. That, most of us, grow up in this arithmetic world, and therefore by this observation of Reed, you might think totally geodesic submanifolds are common, but the finiteness is actually what's generic. And I do want to dwell for a moment on a couple of questions that I like, that I don't think are fashionable enough. And in fact, I think people are oddly dismissive of sometimes. But the first is this question that's in the Gromov and Piateski-Shapiro paper, where they ask, are all real hyperbolic manifolds of high enough dimension built from subarithmetic pieces? The quotes are around those two phrases because those are their phrases. I don't want to ask a vague question on my own account, but I feel that Gromov and Piateski-Shapiro have the right to ask vague questions. In particular, they don't define subarithmetic piece in their paper, although in context, one has a sense of what they mean by it. And I want to point to a much more concrete version of this question that I don't know the answer to and that I think should get answered, which is, if you look at a non-arithmetic hyperbolic manifold of dimension greater than 3, all the examples we know of currently contain a totally geodesic submanifold of codimension 1. Is this because it's a fact or because we don't know a construction? I think that's an important question, and I find out very hard, maybe high enough dimension should not mean bigger than 3, but I find it very hard to make sense of their question without asking this one. This is a question I think deserves research, and I think most people who study hyperbolic manifolds come from the school of Thurston and therefore tend to think the answer to this question can't possibly be yes, because it's not yes in dimension 3. But the reasons for that don't persist in dimension 4 and higher. So I think it's a very mysterious question. And the reason this question is open is because all of the examples of non-arithmetic manifolds we can construct above dimension 3 are variants either of this GPS construction or of reflection group constructions. I'm going to skip over the next 2 remarks on the slide about reflection groups. I was just surprised when learning these things for the purpose of this project that, there are many, many more things about reflection groups that we don't understand than that we do. As a young person, or even as a middle-aged person, I was naive and thought that was a well-understood theory, and it is not. I do now want to say something about complex hyperbolic manifolds. This is the first time I've ever proved a theorem that's actually, when you're proving a theorem, you're often thinking of finitely many examples, but in this setting, I was proving a theorem about, at this point in history, finitely many examples, because there are only 22 known examples of non-arithmetic complex hyperbolic manifolds in dimension 2, and there are only 2 known examples in dimension 3. The early work on this was by Mostow, Deline, and Thurston, who had 3 different points of view, but really gave overlapping constructions of the same examples. I think this 17 is wrong and is actually a 14, for which my apologies, but they found most of these examples in the 80s. I don't want to put on the slides the long list of names I should for all the other people who have worked on this since then. There are, now these 24 examples All examples can be built, as I understand it, by all three of these methods. They all are, all the methods somehow find the same examples once you push on them exhaustively. And this question isn't mine, but is one of the more important questions in the field that I feel I can't talk about complex hyperbolic manifolds and arithmeticity at this length and not mention it, which is just the question is, are there any non-arithmetic complex hyperbolic manifolds in dimension greater than 3? This question is actually related to the one about real hyperbolic geometry on the last slide, just in the sense that the reason why we can't answer the last question and why we can't answer this question are in some sense the same, which is that, we'd like to play games of cutting and pasting along totally geodesic things in the line of Gromov and Piatetsky-Shapiro, and if we can't do that in the complex hyperbolic world because all totally geodesic things are codimension at least 2. And so, the reason we can't construct more real hyperbolic manifolds might be the same one that we can't construct more complex hyperbolic manifolds, but it isn't clear if that's a real reason or just an obstruction to our imaginations. I do also want to mention another recent result by Asnalt and Grushonig that says that, all complex hyperbolic manifolds are integral. This means that, the matrix entries have to be integers, even if they're not all integers, as in the arithmetic case. This is definitely not true in the real hyperbolic world by work of Hegel and Belopetetsky-Thompson. But it's an interesting phenomenon where complex hyperbolic geometry is very different than real hyperbolic geometry. And I just want to, say a few more words about complex hyperbolic geometry, because I want to be able to say some words about proofs and have definitions of some objects handy. So in complex hyperbolic geometry, I have, complex hyperbolic k-space sitting in complex hyperbolic n-space, but I also have real hyperbolic k-space sitting in complex hyperbolic n-space, in this case, up all the way to dimension n. These are the totally geodesic manifolds, or rather they're universal covers of what I'm talking about in my theorem. The CH1 is the hyperbolic plane, but in CHN its curvature is -4, whereas if I took H2 sitting in CHN, it would have curvature -1. And the isometry group of CHN is SUN, and the H2 orbits are SO21, while the CH1 orbits are SU11. And so, this is some picture of the geometry in terms of subgroups. If I want to talk about the proofs are all done in language of dynamics and ergodic theory. The frame bundle of HN is SON1. This is its isometry group. And so if I look at the frame bundle of my compact or finite volume X, it's G mod gamma, where G is SON1. And totally geodesic submanifolds come from orbit closures of the subgroups of the form SOK1, acting on G mod gamma. And you should notice that SO11 is the diagonal matrices, gives the geodesic flow, and so orbit closures of SON1 are the geodesics. But they're the ones we don't like to think about because we want to mention at least 2. For CHN, as I said on the last slide, life is a bit more complicated. SUN1 is the bundle of complex frames, and we can take this group W to be SUK1 or SOK1. So we have this group W in either case, which I'm just going to let K be a variable, or fix K, and maybe fix the form in advance. But this group W is going to be given to us to build totally geodesic submanifolds from. It's orbit closures for this group W. So we're always going to be studying orbit closures of W on G mod gamma. And really, what we prove might be better formulated. The question was asked in terms of geodesic submanifolds, so that's how we state the theorems, and it's natural in that form, but you can state everything and talk about everything in the language of homogeneous dynamics as well. So if we have W acting on G mod gamma as above, we call an orbit closure maximal, again, if it's not contained in a larger proper orbit closure. And the theorem then really just is the form that, if there are infinitely many maximal W orbit closures in G mod gamma, then gamma is arithmetic. This theorem is the same as the other theorems. It's just, formulated in dynamical language instead of geometric language. I do want to mention that the question motivated by Gromov and Patetsky-Shapiro in that form becomes, if n is greater than 3, is it true that minimality of the action of SON minus 1, 1 on SON 1 mod gamma, does that imply that gamma is arithmetic? Maybe it's better to think of it from this point of view than the geometric one. I don't honestly know, but I like this question, so I'm advertising it twice. Is there a question?
No.
So I now want to take the remaining few minutes to say something about proofs, because I am speaking to an audience containing many experts. And the first lesson in the proofs is the lessons from the master, which is what we learned from Margulis in 1974, which is to prove arithmeticity, we prove superrigidity. At the time, this was surprising, but by now one should know that this is a technique one should use. So from now on, G is a simple group, and really G should maybe be SON1 or SUN1. Gamma is a lattice. We have some other algebraic group over some other local field K. And superrigidity provides criteria for when homomorphism from gamma to this other group, and we assume there's a risky dense to again avoid stupidities. When does a Zariski dense representation extend to G? And what Margulis really proved is that, for certain triples, L, K, and rho, having superrigidity implies arithmeticity. And he didn't have to state things with this specificity because, well, he could prove superrigidity for all L, K, and rho essentially, but you really only need some of them to imply arithmeticity. And that's important here and has been important in other applications of this philosophy in the past. And the technical words are you only need L with the same complexification of G, or L absolutely isogenous to G, if you like that word. So from now on we'll be assuming this, but I'll try and be more concrete in what I say. And so I will at least get to state our superrigidity theorem, which is true just for these G's. The L's you have to care about are basically SOPQ and SUPQ. I'm missing some examples this way, but the experts can figure out what they are, and the non-experts would not find it enlightening. And now, we have this totally geodesic manifolds coming from orbit closures of W1 G mod gamma, where GW is some simple non-compact group. And what the theorem says is that if I pick up one of these L's, it's going to come up in my proof of arithmeticity, and I look at any non-compact Zariski dense image representation of gamma into L, this extends to G, provided that for one of these W's and some algebraic subgroup J of L, there's a gamma equivariant measurable map from G mod W to L mod J. This is a slightly strange theorem to have, but it's an interesting theorem to have that might conceivably have other applications. It tells you that, there's some kind of map between equivariant measurable map between varieties that allows you to extend your representation. And that turns out to be enough to prove arithmeticity with. And now I officially have 2 minutes left. And I want to use those 2 minutes and maybe one more to give you some indication of the proof and maybe teach some students some bits of history at the same time. There are 2 steps in the proof. One step in the proof to prove arithmeticity is, well, I better build this measurable map. If I'm going to use this theorem that requires it, I should build that. And then we should study the properties of equivariant measurable mappings between algebraic varieties of this kind. This entire philosophy is, in some sense, the same philosophy that Margulis used in proving his superrigidity and arithmeticity theorems in the 70s. The stranger part from the point of view of the history is that building this first measurable map. For this, we use homogeneous dynamics and study measures on projective bundles over G mod gamma. And step 2 uses ergodic theory of actions on algebraic varieties. I want to just put down the parallel to Margulis's original proof, where we started there with a gamma equivariant map from G mod P to L mod J instead of G mod W, where P here is a minimal parabolic subgroup. Here, step 1 is very easy from the modern point of view. It was harder at the time, perhaps, but from the modern point of view, this is just follows relatively quickly from amenability of P. And the strange thing happening here is that this W is not amenable, and therefore there's a lot more work in step 1. And the second step, Grisha used the fact that the group had higher rank, and some facts about centralizers that derive from that. And he used the ergodic theory of actions on algebraic varieties in a way that, very much inspires the way we're using it, although there have been some significant historical developments along the way. One of them, which I don't think is the most important, but is important to mention just because in rank 1, you clearly can't use centralizers. Groups just don't have interesting centralizers in rank 1. So instead, what we get away with is we get away with using normalizers. If T and G is a subgroup, the normalizer is also a subgroup, and we use structure of normalizers of groups to prove our theorem. I don't know, am I out of time, or do I have another minute or two?
There is no one else to come, so you can continue. So
there's no one else to come, so I can continue. And I'm early in my morning, so I'm just waking up. So I could talk for much longer, but I won't. I want to mention something more about the proof, particularly in the complex hyperbolic case, just because it's an interesting connection. This is some sort of vague outline of a strategy. I should mention here that the way in which we do step 2 uses very much some earlier work Botter did with Furman, where they were basically just trying to understand, the proof of step 2 in Margulis's proof is very short, but not very comprehensible in my mind. I've had many students ask me, what's really going on there? How did he come up with that? And Grisha, when I've asked him, has told me that it's he realized there was a fundamental incompatibility between measure theory and algebraic geometry. I think that is what drives that proof, but Botter and Furman have been thinking about ways to repackage and re-understand that proof for many years now, and I think it has been fruitful. In the complex hyperbolic world, our proof doesn't sort of continue to smoothly follow the lines of Grisha's original proof, even modified. We encounter some kind of obstruction. And from this obstruction, we build a geometry preserving map from the boundary of complex hyperbolic space to itself. And geometry preserving here just means we send the boundaries of complex geodesics of CH1s to the boundary of CH1s. And I just wanted to mention this because, the history of geometry preserving maps is another thing that in rigidity theory has a long history. Probably most famously, Mostow's use of Tietz's theorem to prove the higher rank cases of Mostow rigidity. That work was then extended to prove QI rigidity by Kleiner and Lieb and Eskin and Farb and Eskin. With my student Nguyen and with White, we used the same set of ideas to prove some QI superrigidity theorems. The thing we're actually using here is much closer to these works, where they use the same kind of geometry preserving map to prove various results about superrigidity for maximal representations. This is work of Berger, Yotzi, Pozzetti, and Duchenne, Leclerc, Pozzetti. And we really are using very explicitly in our work a theorem of Beatrice Pozzetti. The other interesting thing is that Margulis and Mohammadi, they used a geometry preserving map to prove their version of the real hyperbolic case. In the real hyperbolic case, we could get away without that. But then when we tried to finish the complex hyperbolic case, it came back. And so perhaps I should end there and just say that, you know, there are lots of interesting questions left here about both superrigidity theorems, arithmeticity of manifolds, and geometry preserving maps of symmetric spaces, which have, you know, some set of relations. Thank you so much for your time and attention.
Thank you so much for a very interesting talk. Thank you. Are there any questions? Hello, are there any questions?
Venki, is it audible? Can I?
Yeah, you are audible to me.
Okay. Yeah. So David, did I miss something? But in this collection of examples of non-arithmetic lattices in CH2, CH3, are there? I mean, do there exist totally geodesic complex one-dimensional gadgets at all?
Yeah. Yes, there are. Well, that's an interesting question. They're built from some sort of reflection group philosophy. And because they are, there will be some totally geodesic submanifolds. When I was in progress, when we were in progress on this work, I asked the same question to Rich Schwartz because I wasn't sure. And I asked him if, you know, if knowing this about finiteness of totally geodesic manifolds is interesting, and he said he thought yes, but you know, you could try and prove this theorem by a different method. Although the different method, it's interesting that that's hard too, right? You could look at these 24 examples, and you could find it just, you know, they're very explicit groups at this point in history. Most of them we know presentations for. You could try and build them and then look for totally geodesic submanifolds, check that there are only finitely many in each of the finitely many examples, and be done with it, not need, you know, methods that are very much transcendental, which we're using. That turns out to be hard as well. It's actually genuinely hard, even given a very explicit example where you can find a few totally geodesic manifolds to show that you found them all. Right? It's easy to find some, and I believe in all the examples, it's easy to find some that are sort of handed to you from the right point of view on the construction. But then you want to prove finiteness. I mean, this was the other thing. I had a funny experience. The first time I talked about any of this, I was talking about the paper with Lafont in front of Shmuel Weinberger, and I was giving some introduction with some motivation, and Shmuel blurted out at minute 3, he said, "What about the Gromov, Piasecki, Shapiro examples?" To which I replied, "Well, that's the theorem, right? You know, you know, even just for those simple examples where you clearly have at least one totally geodesic submanifold, you'd think there might be some naive, easy hyperbolic geometry, you know, soft geometry topology, you know, linear group proof of the finiteness." And, you know, even in that case, our proof uses, you know, some non-trivial homogeneous dynamics. It's, you know, none of these things are, you know, finding a few examples of mirrors that come from the constructions isn't that hard, but proving that all there is not, you know, there are no explicit examples where there's an easy proof of, say, okay, I'll hand you this manifold built this way, and you'll hand me back an easy explicit proof of finiteness. That typically doesn't happen. There are, you know, there are two graduate students of Stover's who have in fact done that for some cusp hyperbolic 3 manifolds, but that happened after our work, and I still know a way to do that even for a compact hyperbolic 3 manifold.
Okay. Yeah. Thanks. Yeah.
So are there other questions or remarks? Well, let's thank David again. Thank you very much. Yeah.
I have some
Raghunath-
comments. Yeah,
David
Can I-
Raghunath wants to ask you.
yeah. Can you hear me?
Yes, I can hear you.
Yeah, okay. You know, if you start with the Gromov separate example, you have two arithmetic groups which are non-isomorphic, I mean, even after commiserability and so on. And they're
Yes.
patched together along a submanifold. That's how the whole thing is constructed. Now, these two arithmetic groups in SON1 gives rise to these two arithmetic groups come from some Q structure, and then you can go to Q root minus 1, and there you get natural unitary group SUN1. From SON1 you go to SUN1, and you can easily construct such a group with in such a way that you get the same group when you go to SUN1. Though there are two Q structures on SON1, but when you go to QI, you can manage things in such a way that you get the same unitary group. Okay, in SUN plus 1, if you like. You have two groups of which are over R SYN plus 1, and they have a common subgroup which is SYN1, and that SYN1 group gives you a SUN1 group, which embeds in SUN plus 1, and you can assume that the SYN plus 1 groups give the same SUN plus 1 group. Thereby, you get a discrete subgroup of SUN1 on the one hand, and a non-arithmetic discrete group of SON1. And you can look at the group generated by this. My hope was that this would give you a non-arithmetic lattice. I didn't succeed in proving it, but this was my hope. I think I managed to prove it was discrete, but that it's a lattice is not so clear. This is long ago, so I might have made a mistake in my proof that it is discrete, but I was hoping that it is discrete, and the group generated will be a lattice. So this was one of the ideas I had. Maybe someone else has also thought about it and thrown it out as not possible. I don't know. So
No, I actually we found this suggestion of yours on a problem list, and I don't remember who we was, and was talking with someone, and they found on a problem list from some conference the same suggestion you just made attributed to you, and so I too have played with this idea of yours, and yeah, it would be great if it was a lattice, but I also could not prove it.
okay.
Excuse me, can I ask a question?
Yes, of course.
Yeah, I'm Sengupta Venki.
Yeah, hi.
Hi. Yeah, so you raised that question about existence of codimension 1 totally geodesic submanifolds in higher dimensional hyperbolic manifolds.
Yes.
So there you assume that they are all non-compact?
The question is for finite volume, including the compact case.
Including the compact case?
Yeah, including the compact case.
No, the reason I'm asking is in the first talk today, Hio told us she was working with compact hyperbolic manifolds, and she showed that the image of a horocycle is a codimension 1 totally geodesic submanifold. I mean, she can correct me if I've understood her statement wrongly.
No, not totally geodesic.
It's not totally geodesic. The horocycle is not totally geodesic.
No, not horocycle. U orbit in G mod gamma, the image inside the hyperbolic under the projection. She showed
It's
totally geodesic submanifold of codimension 1.
It is the closure of the horocycle, not the horocycle itself.
Not the horocycle, the projection onto G mod K mod gamma.
No, the projection of the closure, not of the horocycle.
Okay, the H orbit you mean.
Orbit closure and then project.
Yeah, I don't know what she said, and she doesn't seem to be here right now. She's
Yeah,
heard this
she's
talk
here, she
before,
could have
so
told us.
but I've talked about this question before. I'm quite sure if she knew the answer, she would have told me by now.
Okay.
She and I have talked recently, and she knows I'm interested in this question, and we've talked about it. So I don't know what she said, but I don't think she knows the answer to this question.
No.
At least
Hold
she
on.
didn't
It's
last
Amir
week.
here.
No.
I don't think that's what she said. She said the closure is always a properly immersed manifold, which is always true. That's
Yeah, must be,
Okay.
otherwise that would have answered.
No. Totally geodesic submanifolds of codimension 1 cannot exist even for arithmetic lattices unless they're the specific type of SYN1 with even over the number field. No, those which come from division algebras, quaternion division algebras, they cannot have codimension 1 totally geodesic submanifolds. That's out of the question. If I understand right, that's your question, right, Sangupta?
Yeah, but probably Amir just said, probably she just showed it was a totally immersed codimension 1 manifold. But I thought she said something about totally geodesic.
there's no assertion about codimension. It's just a manifold. You might not have any totally geodesic one. The closure can be the whole thing. You can have. That's all she said.
Oh, so the manifold is not totally geodesic, simply a codimension 1 thing.
No, there's no assumption about the dimension. It's always properly immersed submanifold, but you don't know what the codimension is. Maybe it's the whole thing. Typically, it's the whole thing.
I see. Yeah, I was getting confused with this thing. Thank you for clarifying.
Sure, thank you.
If there are no other questions, let's thank David again. And that closes today's program.